Hey, hello and welcome everyone to our February WMISA seminar. My name is Melanie Finch and I'm the president of WMISA. WMISA acknowledges the traditional custodians of country and their connections to land, sea and community. We pay our respects to their elders, past, present and emerging. As WMISA is an Australasian organisation, I would also like to take this opportunity to acknowledge Maori as Tanata Whenua and Te Tiriti o Waitangi partners in Aotearoa, New Zealand. Indigenous people were the first Australian and New Zealand earth and environmental scientists, and we've got a lot to learn from their deep knowledge that spans tens of thousands of years. The WMISA seminar series is about showcasing the amazing work of women in earth and environmental science in Australasia. All the recordings of our seminars are available on our website and also on our YouTube channel. You can sign up as a member of WMISA, anyone can sign up, to get a notification of upcoming seminars, or you can follow us on Twitter, LinkedIn, Facebook, Instagram, we're everywhere now. That's very exciting. So today I'm delighted to introduce our February speaker, Hannah Power. Hannah is an associate professor in coastal and marine science in the School of Environmental and Life Sciences at the University of Newcastle. Her research interests are focused on the geomorphology and hydrodynamics in the coastal zone, and her research covers a wide range of topics from breaking wave hydrodynamics on sandy beaches to geomorphic change on coral reefs through time to tsunami inundation and modelling. Hannah is a Science Technology Australia 2021 Superstar of STEM and was awarded the New South Wales Young Tall Poppy Award in 2021. Hannah is the founder of the Australasian Young Coastal Scientists and Engineers Conference Series, which aims to connect, foster and showcase the next generation of coastal scientists and engineers. So now I'll hand over to you, Hannah, take it away.
Thanks, Melanie. And first of all, thanks to the WMISA committee and network for, first of all, providing such a great network opportunity and for running such an exciting and interesting seminar series. I always learn something when I come to these. I will make a couple of apologies in advance. One is that my webcam is rather dicey, and if I drop out, I'll try and fix it. And the other one is that I got a bit excited putting this together, and so it's probably a little bit long. So if I could get a bit of a time warning, Melanie, that'd be fabulous.
Sure.
I'd also, before I kick off, like to reiterate that I'm here on the land of the Awabakal people here in Newcastle, and there's such a long and interesting history of the Awabakal people's use and interaction and management of the coast here, and we have so much more to learn from that. I've thrown this together in terms of running through a bunch of different projects that I've looked at and how they all kind of form a bit of a story of how we can better understand waves and wave-related processes to better manage our coastal hazards. And I'm going to talk about 3 different coastal hazards if time permits. So if we start on our sandy beaches, one of the hazards that I'm going to talk about today is wave runup, and that's the highest point up the beach that the waves get to. On rock platforms, we often have a process whereby waves wash over the top of the rock platform, and that can create a hazard in and of itself. And lastly, as I'm sure we're all aware, given the recent events in January in Tonga, we have tsunami as a coastal hazard as well. If we start at wave runup, as I mentioned, this is a process that we generally think about happening on sandy beaches, and some of the key research questions that myself and my group are interested in answering are things like, what processes drive extreme wave runup? And can we better predict wave runup? So I'm going to talk about a few aspects that we've looked at in terms of these processes. But first of all, how do you measure it? Well, we tend to do experiments like this set up on the beach where we put a whole bunch of gear out to measure a whole bunch of different things. One of the things that we use is a pressure sensor that we deploy on the sand or under the water on a post or on a chain like this one here. And it simply measures what the pressure is, whether that's the air pressure or the pressure at depth if it's under the water. And we can convert that to a depth or a height of water above the sensor. And we end up with something like this. A time series of what the water surface elevation looked like through time, and we can pick out the wave crests, and we can pick out the wave troughs. We can also use LiDAR or laser scanners. We tend to, in the coastal realm, do a lot of, and I guess a lot of people in science do this, using things for not their intended purpose. So these laser scanners are designed for monitoring things like conveyor belts in assembly plants to make sure that items are in the right space, but we can actually repurpose them to get a full scan of the beach up to 25 times a second. And we can use that to measure wave heights and beach levels or sand levels on the beach as well. And then one of the key tools that I'll talk about, some of the data that we collect using this system, is a video camera. And we simply use a sort of standard consumer grade handheld, handy cam type thing. And there are a few different things we can get out of the images that we get from a video camera. We can take an average image over time, so take all the sort of frames out of a series of video and average them to get an image like this, where we see where the sort of fuzzy white is where the waves are breaking and where the blue is where the waves are not breaking. But we can also do a little bit of image trickery, and we can take the images, which are typically oblique, we can transform them so that they look more like a plan view, so as if you're looking top down. And then if we take a single line of pixels out of each of those transformed images, so say, for example, that represents this black dashed line here, we can take one of those lines of pixels out of each subsequent frame, and we can create an image like this one here, which is a time stack in the top right. And what this represents is an example of how the waves behave along one line in the cross-shore direction through time. So each one of these white lines that you see here is the process of a single wave as it moves towards the beach, runs up the beach, and then reaches its maximum run-up point and runs down. So this image isn't like a snapshot, it's like a time series, but with pixels derived from video data. And we can see that different waves get to different points up the beach, and this wave here is the highest that we have in this 300-second time period. So one of the things that we were interested in doing is using these kind of time stack images. And again, we're looking at the same kind of thing. Sorry, I'm having some technical difficulties here. And pulling out the highest point that each wave gets to on the beach. So that would be these red dots that you see here. And from a management point of view, we're often interested in capturing this kind of data. And we can do it, as I said, via video. We can also do it using those laser scanners that I mentioned before. And we're interested in obtaining the vertical elevation, so how high up the beach each wave is getting to. And from a management point of view, we want statistical descriptors. Having all this raw data is not super useful. So over a given time period, we tend to calculate two parameters. One is the level that is exceeded by only 2% of waves over a given time period. So if you had 100 waves, it's the level exceeded by the top two. And then within a given time period, we also calculate the maximum run-up. So this is this parameter here, and that's the highest point over a given time period. And obviously, the longer you observe for, the bigger that maximum run-up is going to be. So what processes actually drive extreme wave run-up? Well, some of the processes that we've looked at are our offshore wave conditions and local conditions. So what's happening in the deep water? Is it a day with really big waves offshore or really small waves? And then we also look at local conditions like, what does the beach look like? Is the beach really eroded? Does it have lots of sand on it? Those kind of things. So this includes looking at things like wave height, wave length, and wave direction offshore, because the direction of the waves relative to the orientation of the beach makes a difference. And the local conditions include things like beach slope and morphology, so the shape and the orientation of the beach. But one thing that often isn't considered when we look at wave run-up, and this is one thing that we worked on recently, is what happens to a wave prior to a run-up event. So waves have a history. They arrive at a beach, they break, they move across the surf zone, and then they run up on the beach. And so we can sort of depict that here, where we have the point where the waves shoal, they sort of peak up, they break, they change rapidly in shape immediately after they break. Then they might travel across the beach for a bit, running across the back of previous waves, and then eventually they run up the beach. And we're interested in understanding what happens out here that might influence what happens in here. So one of the things that happens in the surf zone is that waves interact with each other. And you might have seen this if you go down to the beach, you see one wave overtake another wave that's in front of it. And this process is really interesting because we can pull it out in our time stack images. So we've got a time stack image here, and each colored line represents the path of each wave. And anytime these two paths cross, it's because one wave has overtaken another one. So if we look at this example here, we've got this purple wave coming in, it's traveling relatively slowly. This red wave coming in behind it, it's much bigger, it's broken further offshore, and it's traveled faster and it's caught up to this purple wave here. And so it's overtaken it and captured it, and then we just have one wave moving on from there. And so what we find is that these capture processes actually drive extreme wave run-up events. And we found that 97% or more than 97% of our extreme shoreline maxima, so our highest run-up events, were driven by waves that had undergone bore capture. And we can really clearly see that here in this sort of 300-second capture. We've got the shoreline mapped out in black, and then we've got wave capture events identified by these red boxes. And we can really clearly see that it's these waves that have undergone this capture process that lead us to these really big run-up events. So identified by either the yellow or the yellow and pink circles. And so this kind of helps us understand what actually drives these extreme run-ups. And if we look at what happens on different beaches, we see the same process again and again. So if we look at where each wave gets to across the swash zone extent, so that's the sort of part of the beach that's wet and dry intermittently, we see that waves, here's a whole bunch of 6 or 7 different beaches, 6 different beaches and an average. For each beach, the waves that have undergone capture events make it further up the beach. So this is one really interesting thing that we've found recently. So that leaves us to another question. Can we better predict wave run-up? And if we look through all the literature, we see that there have been a multitude of predictors for wave run-up. And here's a series of different equations that predict that 2% run-up exceedance level. So the vertical elevation that's exceeded by only 2% of wave run-up events. And I'm not going to go through what each of all of these mean, but suffice to say, there's a lot of variability here. And most of them, when we actually test them against data sets, are subject to large and really variable errors if they're uncalibrated. And we can see that there are a lot of constants in these equations, and they're often derived from best fit type processes associated with a particular data set. So when we look at what the error is for a whole bunch of these different models, and each one of these series of letters across the x-axis represents a particular wave run-up model. The y-axis represents the error in meters in the vertical, so not meters in the horizontal, meters in the vertical. We see that even our best performing models still can have significant errors, so like 23% on unseen data. And this is really problematic. If you're thinking about a beach that maybe has a slope of 1 in 50 or 1 in 100, a 23% error can be of the order of sort of 25 to 50 meters in the horizontal. We're talking really significant errors here. So what can we do? Well, we can take existing predictors and we can optimize them and calibrate them for a particular site if we're working on one particular beach. But often we won't have a really large data set, and also beaches change with time. So if we collect data on one day and then we try to apply it for a different scenario on a different day and the beach has changed in between, well, that can be really problematic and can lead to errors that are just as large as an unoptimized and uncalibrated model. So as I said, it requires locally measured data. This is also often just not available. We can get equal or improved performance by optimizing and calibrating. So we might increase our correlation values by about 6% and decrease our error values by about 16%. But there's uncertainty around the value in this. As I mentioned, if you calibrate on data from one day, how good is it for predicting run-up on another day? We can use machine learning techniques, which we can use on really large data sets, and we can use these to develop some more accurate predictors. So this is one thing I trialed a couple of years back, And you end up with really hideous equations like this, right? But ultimately, this is just a really long equation. It doesn't have anything overly complex in it. It's exponentials, it's logs, it's addition, it's subtraction. And when we look at those previous equations that we had before, none of them are ultimately based on an understanding of the physics, and nor is this, right? So we're just fitting data to our runup. But when we use some of these machine learning techniques, we can actually get some better predictors. And while we still require data to test or calibrate, we can improve performances by about 10%. So there are some advances that we're making in this field in terms of improving our predictions of runup using different techniques and novel techniques. So from this kind of aspect of my work, where are we going? Well, the majority of our observations of wave runup are made from either moderate storms or our sort of everyday conditions. And there's a really big question around this. Can we extrapolate these sort of everyday conditions to extreme storm events? And one of the really big problems here is issues with dunes. If the waves start to hit the dunes, they start to erode the dunes. We also truncate our runup. It doesn't reach its full potential, you might say. And so that then changes our equations completely. So there are some real challenges there. The other challenge is that most work focuses on cross-shore processes. So looking at just one line across a beach rather than looking at the length of the beach. And so we need to consider this variability of runup in the alongshore direction. So if you go 50 meters to the left or 50 meters to the right along the beach, how does that vary? How does that alter your runup? And as I mentioned, model predictive skill varies really significantly. So this is something that we really need to work on, and it varies both between and within the science. And while it almost always improves with optimization, we've still got a really long way to go there in terms of coming up with really good models to predict wave runup. As I mentioned, machine learning can provide some gains, but it's certainly not perfect. And we need to further understand processes to improve our runup predictions. So moving on to something really different now. This is some work that I did with a project with colleagues at the New South Wales, it's now Department of Planning and Environment, a couple of years back, looking at wave overwash on a rock platform. So we've now moved from sandy beaches to our coastal rocky shores. And the key questions we're interested in for this project were what conditions drive overwash on rock platforms? And can we predict when the conditions are going to be really hazardous? And this photo here is a great example of conditions that are hazardous. You don't want to be on this rock platform when this is happening. So this was a very site-specific study. It was a study of the figure 8 pools, which are in the Royal National Park south of Sydney. And they're these rock pools that have been ground down into this sandstone rocky shore platform. The reason for the focus on this site was that these pools that you see here, in particular this one, that's the sort of figure 8 shape, became very Instagram famous and went from having, a few thousand visitors across a summer to having, in excess of hundreds of visitors in a day, because everyone wanted to come and get their photo in this pool. Access to this site is really limited. It's a long bushwalk. There are no amenities. If you're not someone who's an outdoors person, it can cause some problems. So we used similar techniques to what I've talked about before. We set up some cameras. We wanted to have sort of low impact in terms of the visual amenities. So we did some home paint camouflage jobs on them. And we got out the same kind of data that we look at on a beach. We use the same techniques. So we're looking at a time stack again here where time goes down on this graph, and the distance across the platform is across here. So to the left of the 0, these are waves off the edge of the platform. So these are waves hitting the edge of the platform. And then you see every now and then a wave breaks over the edge of the platform and comes across the platform. And different waves get different distances across shore. And from memory in this graph, that figure 8 pool sits at about 18 meters. So it sits somewhere here. So in this time period that we're looking at here, there'd be 6 events reaching that pool, but they're not traveling a huge amount further than the pool, so maybe they wouldn't be too hazardous. So we used about 8 months worth of data and looked at that data to pull out some information about how far across the platform the waves were getting. And we used a combination of the lightness of the pixels. So are they very light like these white ones, or are they dark like the dark ones? But we also combined that with color temperature. So is the pixel color warm or is it cold? Because the water tends to come up as a colder color than the warm rock when light reflects off the rock. And so we were able to come up with sort of thresholds to say how inundated over a given period of time is this point on the platform. And that's what you're looking at here. It's just kind of a summary of everything that we saw in this time stack. It represents that full width of the platform. We can see this really sharp change in our metrics at the edge of the platform. And we can see where this sort of maximum limit of wave activity ends within that graph. And combining these two variables, we were able to come up with a really automated way to analyze 8 months of data, which was really an enormous amount of data. We calibrated our camera methods using, again, pressure sensors. And we did a really high-tech job here with a whole bunch of dive lead and gaffer tape and cable ties, and it works a treat. And if we compare what we measured out of our pressure sensor, so you can see all the peaks here correspond to a wave washing over the platform, with our peaks in our light intensity, we see that they match up really nicely. So we're really confident that our remote sensing techniques correlate well with more in situ observations. And what we got out was a whole bunch of different sort of levels of inundation. And each one of these colored lines represents a time period where the hazard is different. So the black one, the black one here, we see really no impact of waves on the platform. It increases to yellow, orange, red, and purple. And this Y scale here is really just a measure of the percent of time that the platform is inundated based on those remote sensing measurements. And from these different measurements, for every hour of daylight that we had for over those months, we had one of these lines. And so we're able to then categorize these lines into different categories, depending on how far the inundation got or the waves got across the platform and how frequently they got to different distances across the platform. Because we're interested in not just, well, is one wave getting across the platform during the whole time, or are there lots of events? Because we're really interested in trying to categorize hazard here and then look at risk to people. So we ended up with 5 different hazard categories, ranging from low through to moderate overwash through to extreme overwash. And then we used those data to come up with a time series. So we've now got a time series of hazard category from very low hazard at A through to high or extreme hazard at E. And here's the first month of data, but we had 8 months of this data. And when we compare these hazard categories to our conditions offshore, the blue line here is our offshore wave height, and the orange line here is our offshore wave period, so how frequently the waves are arriving. We see that, and if we look at our mean wave height, we see that really anything above an average wave height results in really hazardous conditions at this particular site. So in general, this is a very hazardous site. And we were seeing that in terms of prior to this work being done, we were seeing that there were significant emergency responses needed in terms of people needing to be helicoptered out and ambulance teams having to walk in to treat people so that they could then walk out. So there was a real need for something to be done in this space. And so what we did was we took our forecast wave and tide conditions and we added them to our thresholds from our observations. So we combined all of this information, and that allowed us to develop a warning tool that allows us to take our forecast, use our thresholds based on our observations, and provide a forecast of a warning. And that's now live on the National Parks and Wildlife Service website. If you go to the Figure 8 Pools website, what you'll see is a risk forecast. And it gives an hourly risk forecast for a 4-day period, and it tells you what that means. So in this screenshot here, at 7 p.m. on this particular day, the risk rating was extreme, and it gives you information about what you should do. And obviously, if it's extreme, don't go there. So this is an example of where we can use science to solve a problem where we're seeing real risk to communities and real risk to visitors to our coastline. But this was one particular site. So there's a lot more we can do in this space. So we were able to demonstrate that remote sensing offers excellent opportunities to obtain data in what's otherwise a really challenging environment. And I think some of those photos I showed give you a feel for how energetic that environment can be in terms of deploying in situ instruments on that platform. But it is really necessary to ground truth all that data. And we did that with those sensors in the pools. Certainly rock platforms are far more challenging for sandy beaches for remote sensing because of the changing colour of the rock and the algae and light reflecting off the pools. There are a whole bunch of things that made that work really challenging. But we're able to show that it is possible to forecast wave risks on rock platforms, which was a great success. Site-specific data is really critical in this space, and this platform is a really unique shape. It's got some really unique morphological features. And whether or not what we developed here in terms of exact thresholds is transferable is something that we need to do more work on. And we need to do some more work also on understanding these issues more generally. So how does the morphology and the orientation of these rock platforms affect how often they're overwashed by waves? So that's a brief intro to some of the work we've done on rock platforms. And the last one, just check on how I'm going for time, I'm not too bad, that I'm going to talk about is around Tsunami. And I kind of threw these slides in because of everything that's happened in Tonga and because of a couple of radio interviews that I did in the wake of that, where people said, okay, but what's the actual risk of tsunami to Australia? And I think these newspaper clippings from 1960 sum it up really nicely, because these were the headlines that appeared in the papers after the 1960 Chile tsunami that was derived from the earthquake that they had. And that earthquake was one of the largest 5 earthquakes we've recorded. So this was a really significant event. And so a couple of the research questions that myself and my team have been working on in this space are, what is the risk of earthquake-generated tsunami in our estuaries in particular? So we have an understanding that there's a risk in the open coast, but what about in our estuaries? And then we often think about tsunami as being generated by earthquakes, but they can be generated by other sources. And so another question that my research group have been looking at is how hazardous a submarine landslide generated tsunami for Australia? So I'll have a bit of a chat about each of these things. So tsunami and estuaries are interesting because estuaries are often very complex features morphologically. They're often very unique in terms of their morphology. And so we often have a need for very site-specific information. And this can be really challenging because we don't often have really good data in terms of the depth within estuaries. We do now in New South Wales as a result of some work that was done in 2018, where we flew terrestrial and marine LiDAR for the whole of the coast. But it doesn't exist everywhere, and it certainly doesn't exist in developing countries. But because estuaries are so complex, there's often a need for really detailed models. And so you can see here the outcomes from some of the models that we've run for Sydney Harbour. I'm going to talk about this a little bit as a bit of a case study. So Sydney Harbour is a drowned river valley. It was a river valley during the last glacial maximum when sea levels were 120 metres lower than they are today. And as sea level has risen to its present day level, it's been flooded. And so we've ended up with all these really complex bits of shoreline. Sydney Harbour's got 2 main thalwegs, the main arm of the harbour, which comes down and ends up at Parramatta, and then the northern thalweg, which is often referred to as Middle Harbour. And what we're looking at here are the outputs from basically the largest event that we modelled. So this is the result from a magnitude 9 earthquake on the Paisiga Trench to the south of New Zealand, and the potential for what we would see in Sydney Harbour. And the colours here represent the maximum water level above mean sea level. And you can see that our scale ranges from 0 up to 8. And then areas where it's coloured sort of inside of this mean sea level coastline, which is the dark grey line, are areas where we would likely experience some inundation. And we can see that there are some particular areas of concern, the main being Manly Corso here, which if you've ever been to Sydney and you've taken the ferry to Manly and you've walked across to Manly Beach, you walk across this stretch here. We see some really significant inundation here at Balmoral and around, this is a suburb called Clontarf here. And then also in the ends of some of our little arms of the estuary. So around sort of the Glebe foreshore area here and Pyrmont, and around some of these other areas here around Haberfield and Leichhardt, for those of you who know Sydney. But what we see is really different behaviour of the tsunami wave in the different arms of the river. So if we look at the south arm, which is this solid pink line, or the main, having some computer difficulties today. If we look at the south arm of the river, and we look at how the maximum water level above mean sea level changes as we move from the entrance on the left to upstream on the right, and these are sort of flipped to the figure on the left, on the right, we see that as our events increase in severity, so we move from a sort of 7.5 magnitude earthquake on the Bysiger Trench down here in the yellow, through to an 8.5 in the orange, right up to our 9 in this blue, we see that the maximum water level above mean sea level that we would experience along the central line of that channel increases. And this makes sense, this is what we would expect. And for this south arm, we can come up with some sort of fairly basic rules of decay. As wave height increases at the entrance, it tends to follow a approximately straight line as we move upstream. And so we can come up with rules of thumb that describe these kind of impacts. In contrast, if we look at the north arm, we see that things are completely different. So we're now going up through here along this dashed pink line, and we see that there are some really interesting things happening in this stretch between the sort of entrance to Middle Harbour and Spit Bridge. And we see a lot of amplification of the wave, where we're seeing wave heights in here that are much greater than wave heights at the entrance. So this really highlights the unique nature of estuaries and how each different part of each estuary behaves really differently. So while we might be able to develop some rules of thumb for the main arm of Sydney Harbour, it's much harder to do so for the arm going up through Middle Harbour. And just to give you a feel for what this might look like, because it's quite an interesting aspect of the model that we were finding in the Manly Corso region, is that what we have is not just waves coming in from the ocean side, but the wave comes into the harbour, wraps around North Head, and then inundates Manly Corso from a sort of westerly direction. And if I can get this video to work, hopefully, you'll see that happening in the top right there. And this model is a really high resolution model, and you'll see that we've actually modeled buildings and streets, and you can see the influence of that where water flows down the streets. But we're looking at potentially, 1 to 2 meters of water crossing Manly Harbour in this sort of most extreme event. So again, this is the magnitude 9 earthquake on the Bysiger Trench. I'll just play that again because everyone loves a good little video. But yeah, you see, and the other thing to note is that it's not the first wave that does the majority of the inundation. It's sort of the second or the third wave that comes through that creates that greatest inundation that we see there. So some takeaways from tsunami modelling there. So that's a bit of a quick overview of some of the work that we've been doing on earthquake-generated tsunami, but moving on to something a little bit different in terms of submarine landslide-generated tsunami. Now, you may or may not know, but we have a whole lot of submarine landslide scars off the east coast of Australia. They mostly sit between about Jarvis Bay here in the south, up to, this is New South Wales, but they get up all the way to Fraser Island in southeast Queensland. And you can see each one of these mapped out below in these little grey areas. The grey areas represent historic scars, so where we can see material that's been removed from the continental slope. And these are in depths of sort of 500 to 2,000 metres or so, or even deeper. The red shapes represent areas where we can see material that looks like it has the potential to slide. So there might be some tension cracking at the head of the area, there might be some undercutting of the toe, a bunch of different characteristics that suggest that this is a potential submarine landslide. And if you look at the scale here, you can see that these are big. We're talking, some of these, like this one here is the Bulleye slide. We're talking sort of tens of kilometres long, several kilometres wide, and thicknesses of several hundred metres. So cubic kilometres of material have been removed from our continental slope. So we've done a bit of work looking at whether or not an event like this would have the potential to form a tsunami. If it did, what the impacts would be, and which areas in particular would be most vulnerable. So again, another little case study. This is the Byron slide. It sits off Byron Bay. It's in sort of 500 to about 1500 metres of water here. And we can see in cross-section, this red cross-section here, the thickness here, we're sort of at 800 metres depth up the top here on the sort of flanks of the canyon and flanks of the slide, sorry, and then at about 1100 metres depth here. So we're talking 300 metres of material in terms of thickness and a sort of size of about 5 by 5 kilometres. So again, this is a really large feature, and this is not one of the biggest ones. So one of the challenges with looking at the potential for whether or not these could form tsunami is that we actually have really limited data. We don't have at this stage any maps showing where any of this material has ended up. At this stage, it's either off the edge of our high resolution multi-beam mapping, so it's somewhere out beyond where we've mapped well, or it's been removed, and so there's no trace of it left. So that is a challenge in terms of constraining our models, because we can model where this material ends up, but we don't really have anything to compare to. The material that's been removed, we also don't know what sort of properties it had. What was its density? What was its grain size? All of these things we don't know because we don't have that material. But what we can do is we can take cores from within the slide, and you see these 3 cores, these 3 points here showing locations where we've taken cores, and we can take cores from either side of the slide to get some of that informational representative information. And if we take some of that and we model it for the Byron slide, we end up with some results like this. And this figure's got a lot of information on it, so I'll talk through it. So the slide here is shown in grey, and the darker the grey, the thicker that part of the slide. So as I mentioned, it's sort of up to a couple of 100 metres thick at its centre. The blue shading throughout here represents the maximum wave amplitude that would be generated if we were to have this material all go at once. We can see that wave amplitudes right in close to the toe of the slide get upwards of 10 metres. So we're talking a really sizable wave here. Because of the way the slide goes, it goes down slope, the main wave actually travels to the east. And so it travels away from the coast, but it does refract around, and you can see that here as it moves to the north and moves to the south of the slide. Then all of these coloured dots along the coastline represent a few different things. The first line of dots, the line of dots closest to the coastline, represent a maximum wave amplitude at the coast. And anything above red is 3 metres. Anything that's red is 3 metres or above, sorry. So again, we're talking sizable waves at the coastline. And it's worth remembering that tsunami waves, a wave height of 3 metres for a tsunami wave is much more significant than a wave height of 3 metres for the kind of everyday wind waves we have along our coast, because the period of these waves is different. And so they bring so much more energy and so much more water to our coast. The green shaded dots represent maximum water velocities that we would experience. So how fast the current speeds would be. And you can see that in places we're getting upwards of 5 to 10 metres per second. For a sort of point of reference, an Olympic swimmer swims at about 2 metres per second. You can do 50 metres in 25 seconds or thereabouts. So we're talking sort of, up to 5 to even 10 times faster than that kind of speed. These are not things you want to be involved in. But one of the real challenges with our submarine landslide tsunami is these arrival times, and these are shown by these coloured squares. And you can see that at Cape Byron, the arrival time is of the order of 17 minutes. So unlike a tsunami that would be derived from an earthquake on, say, the Pacific Trench to the south of New Zealand, where it has about a 1.5 to 2 hour travel time to get to New South Wales, in that case, we've got sufficient time to warn everyone. In the case of a submarine landslide, we're really going to struggle. And so our to the best of our understanding at this stage, what is likely to trigger these events is probably a large earthquake. So if you're along the coast and you experience a large earthquake, take that as a sign that there might be a tsunami coming and move to higher ground. And then bringing this back to what we talked about with our earthquake-generated tsunami, what we see is that, again, our estuaries are our most vulnerable regions. So here we have 3 locations within that Cape Byron or Byron area study site. We've got the Brunswick River, we've got Moville Creek, and we've got Belongil and Tallow Creeks around Cape Byron. And you can see from these colours, with red being more severe, that we get much more inundation associated with where our estuaries are. And this is simply because, in general, the land is lower lying, and also because our estuaries provide a little funnel or an access way for water to get into our coastline and affect our coastal regions. So where to from here in this space? Well, as I mentioned when I talked about Sydney Harbour, we've got real challenges with generalising our observations and our results from our site-specific studies to rules that we can apply elsewhere. And the costs of doing detailed modelling like we did for places like Sydney Harbour are prohibitive for so many places around the world. We can develop rules of thumb. As I mentioned, we can develop those rules of thumb that apply quite well for the main arm of Sydney Harbour, but they're limited in use in that even just next door at Middle Harbour, it's not applicable. And so we need something in between. And so this is something that we've been working on that I hope will be published soon. And that's looking at ways that we can use really quite crude morphological parameters. So is there a pinch point in this estuary? Is there a big hole in the estuary? Some really basic bathymetry data in our estuary to derive something that allows us to sit between this sort of rule of thumb where we're drawing a straight line between a wave height at the entrance to an estuary and an upstream point. And then the other extreme, which is sort of very detailed numerical modelling of what the inundation would be. So we're working in that space. And then in the submarine landslide space, we're really in need of more data. We need to look more at how frequently they occur. We've got a sort of window of about a 1 in 9,000 to 1 in 60,000 year recurrence interval for these. And that's a pretty big range. We're talking, something that we might start to worry about to something that you just think it's so infrequent, it's probably not worth worrying about too much. We also really need to constrain our landslide speeds. So we don't know how fast this material moves when it goes. And this is something that's really limiting our modelling. So finding where this material is deposited will really help constrain our modelling. And on that note, a few of us will be at sea in May and June this year, hopefully getting some data that will help us answer these last 2 questions in regard to submarine landslides, along with a few other things. So I'm going to finish with the science there, but I'm going to take a bit of inspiration from some of the previous talks that I've seen in the WMESA seminar series and talk a little bit, very briefly, because I'm a bit mindful of time, about my career journey to date, because it's all well and good to sit here and share a whole bunch of research outcomes and be like, yeah, I've done amazing stuff, I've done really cool science, I've had fun along the way, but it doesn't necessarily show or share the true journey. So I've kind of called this touring the East Coast because I've done a lot of up and down along the East Coast of Australia. And I started in Sydney doing an undergraduate degree in marine science there. I found the sort of coastal marine geoscience space in my undergraduate degree. I didn't even know it was a thing. I went in thinking I'd be a marine ecologist and then realized there was all this other cool stuff that you could do in the marine and coastal space. I did an honours year there and loved it and thought, this is amazing. I can spend my work time going to the beach. I've got my life made. And so I went up to Brisbane to do a PhD, and I did a PhD in the coastal engineering research group there. The kind of work that we do on sandy beaches tends to sit somewhere in the coastal geoscience, fluid dynamics, coastal engineering, civil engineering space. People come at it from a lot of different places. And then when my PhD ended, I came back to Sydney. And at Sydney, I started a 1-year contract as a lecturer at the University of Sydney. And I thought I'd talk about my feeling of success, not necessarily true success, but how I felt in terms of how successful I was being post-PhD. And when I started at Sydney, I had a standard academic 40-40-20 role. And it was a seriously steep learning curve getting to grips with teaching. And so I really felt like in terms of success, I wasn't really going anywhere. Unfortunately, due to a whole bunch of different issues, my contract at Sydney wasn't renewed, despite some sort of talk that it probably would have been. And I scrambled to find work with a really short period of time, and I know that other people in this series have talked about the challenges of short-term contracts. And for 6 months, I did 3 different jobs between Sydney and Wollongong across 3 different universities. And I really felt like I wasn't going anywhere at this point. And in that time period, I thought, you know what, this is not working, academia isn't working, I can't do the short-term multiple contracts, commuting between Sydney and Wollongong, too much, too awful. And at the beginning of 2013, I took a job at Geoscience Australia, and so I moved to Canberra. So I moved away from the coast, and I spent a year at GA, but I was really still wanting to do coastal research, blue sky research, and wanting to, continue what I'd started to do in my PhD. And so in terms of my sort of research career success, I really, again, didn't feel like I was achieving what I wanted to achieve. And I'll come back to the sort of importance of what I felt I wanted to achieve and what my measure of success was in a minute. And because I really didn't feel like I was doing what I needed to, or I wanted to be doing at GA, I took a short-term contract at the University of Newcastle. I took a 12-month maternity leave replacement contract. I left a permanent job in government for a short-term contract back in the university sector. So I did a bit of an about face after leaving the university sector because of short-term contracts. I realized maybe doing what I really want to be doing is more important than job security, at least for me in my situation. And I started there on a 12-month contract. And again, in that first 12 months, I really didn't feel like I was getting much done. But I managed to negotiate another 2 years on my contract, and I felt like things were starting to progress. I won my first major research grant as the lead CI. I started to get some PhD students. And so I really felt like I started to make some progress, and I started to build a team. And coincidentally, my team seems to be about 90% women, which is not something that I've intentionally gone out to do, but it's an absolute delight to have amazing women around me. And at about the 2.5-year mark after having been at Newcastle, I managed to have my contract transitioned over to an ongoing role. And so I really feel like things have started to pick up since then. And in that time, since being converted from contract to ongoing, I've really thought about what things I wanted to contribute to the community. And Melanie mentioned it in the intro, in my bio, that one of the things I've been doing has been working in a whole bunch of different spaces. And so as an example, I'm now co-supervising a student at the University of Tasmania who's doing work on sea level rise in estuaries. And I get to go and do amazing things down in Tassie with her. I've also gone off and done other things that I think might contribute to the community more than just blue sky research. And so we set up the Young Coastal Scientists and Engineers Conference. We ran it first in 2020 when we thought originally we'd run an in-person conference, and we had the mad transition to online because of COVID. We're running it again this year for its 3rd iteration. So please check us out on social media and our website if you're interested in coming along. We hope again that this year we'll be able to keep registration free and really try to build that network for younger people. And since then, success has kind of come. And I'd love to say I have great lessons as to how I've achieved this success, but I think actually really just pursuing the things that I wanted to pursue and contribute to the community have resulted in that. And I was, as Mel mentioned, I applied and was successful in applying to the Superstars of STEM program, along with Mel, who's a fellow Superstar of STEM. And I've also had a couple of awards in the last couple of years. And some of them are things I've put myself out there for, and some of them are things that were completely came out of the blue. I've no idea who nominated me as a Hunter Hero from the Newcastle Herald, the local newspaper. But, that happened, and it was an absolute privilege to be nominated. But going back to that idea of success and thinking about what success really means, I think one of the things that in this sort of flatline period where I felt like I was not really achieving anything, one of the things that I was actually achieving was I was becoming known, and I was building networks, and I was building skills. And so in that first sort of, I guess, 2.5 years post PhD, where I worked across, I think, 5 or 6 different jobs, I ended up taking on some contract lecturing at ADFA in Canberra when I was at GA because I really missed teaching, so I built networks, I met people, and as a result, when I started at UON, I had a whole lot more skills and a much bigger network than I had when I'd left my PhD. So in reality, and I haven't drawn a sort of revised success graph, but I actually don't think that flat line was a flat line because, for example, I learned how to do tsunami modeling at GA, and I wouldn't be doing the work and research I'm doing today if I hadn't learned those skills and I hadn't built that network in Australia's tsunami research space. So I think there's often, I guess what I'm trying to say is that even though you might not think you're achieving things, in hindsight, you might actually be achieving things that drive success later on in your career. So sometimes these things and this success is actually kind of hidden, and it's not something that we see in terms of our metrics in publications or grants or these things that are constantly in our face. There are other measures of success that I think are worth considering. And on that, I think it's worth saying some really big thank yous to all the colleagues who've contributed to the work that I've shown, whose figures I've shown, whose photos I've shown, my PhD students, my collaborators, and all the volunteers. When we go and do beach field work or field work on rocky shores, so many people volunteer to help us get our gear in the water and manage all of that. So a huge thank you to them. And there's some of the papers that I've referenced through this if you want to have a bit more of a read. And thanks everyone for coming along and listening today.
Thank you so much, Hannah. That was so interesting and eye-opening. It was, really wonderful talk. We'll take questions from the audience now. So you can ask your questions by unmuting yourself and hopefully, and maybe turning on your camera, and then hopefully I'll see you. Or you can pop them in the chat and I will read them out. That's another option as well. Marissa?
Hello, Hannah. Thank you so much for that wonderful talk. So many things I wanted to ask you about, but well, firstly, I'm a geologist and a paleontologist, so I think about coasts and coastal processes, but on a totally different scale to what you do. And there was a funny moment at the beginning where you were showing these graphs and the scale. I totally missed the scale on the bottom, and I was like, hang on a second, oh, that's in seconds. Like usually I'm thinking on scales of like hundreds of thousands to millions of years. And so it really just blew my mind a little bit that all of this data that you can collect, like that I just totally miss. And but I had a question about the Byron slide, the landslide. Did you say when that happened? Do you know about when that actually occurred?
So I don't have the date off the top of my head. We have dated it, and it's within, the Byron slide is within radiocarbon range. Okay. So we have dated it. Yeah. I want to say it's like 35,000 years old, but I could be wrong there. It's in the paper.
You know how they date?
Some of those we've dated about 10 or 15 slides along that stretch of coast, and about half of them come back in radiocarbon age. So we're getting that, it's an ongoing process, but we certainly think that, our sort of upper estimate of recurrence interval is based on a sort of, all of these had to have happened within, sort of recent years, because we're still seeing these scars there. They've not been eroded, the features haven't disappeared.
Yeah. And so I was just sort of wondering about being able to log that event, because if you can see or you can model how far these waves can come inland, then perhaps you can see in the record some deposits, deep sea deposits like foraminifera and things like that. Perhaps that can be evidence.
So that's a great question. And one of the big, I guess, challenges in the tsunami record in Australia is interpreting geological evidence of tsunami. It can be quite controversial. The caveat with that modelling that we've done is, that slide occurred during the last scale sea level maximum when sea levels were 120 metres lower, but we're modelling the topography of today.
Yes.
One of the reasons we're doing that is for hazard modelling purposes, to say, okay, if something similar were to happen today, what would the impact be? So it's a bit of
okay,
in a sense, it's a bit of a false scenario.
Yep.
But having said that, right next to the Byron slide is the Byron potential slide that is about the same size and has the potential to go. So it's really about trying to understand what the impacts would be today on our coastal communities if we were to experience a similar slide. And we're using those historic slides because we know they've happened, right? They're a real scenario.
Yeah, cool. Thank you.
No worries.
Cool. Alanis, did you have a question?
Yes, thank you so much for your talk, Hannah. I have a bit of a different question, more kind of around what's happened recently with Tonga and how you found actually like talking to the general public and like what kind of their reaction was to it. Like, were they quite receptive to it or not really?
Yeah, so I had a bit of a media blitz post the Tonga tsunami. I posted, it happened late on Saturday. I know where to pull up tide gauge data and so on. And so I just started posting some tide gauge data up on Twitter, and it kind of blew up a bit. That wasn't my intention or what I was expecting. ABC, pulled one of my tweets and put it on one of their news articles. And then I was getting calls from journalists, which again, like I said, I was not expecting or intending. In general, I found everyone to be really receptive and wanting to learn more. It's not very often that we experience a volcanic eruption of that size. It's certainly the biggest tsunami we've measured on the Australian coast since 1960. So in that sense, it was a really rare and unusual event. And something, most people haven't seen in their lifetimes. So people are keen to understand. I think one of the things that I certainly noted talking to a few people, and I was on holidays by the beach at that point in time, so I sort of had to put my holiday on pause for a little bit, but talking to the locals in the area where I was, on Sunday morning, they went out for a swim and I was saying, well, but the tsunami warning is still current, this event is still ongoing. And I think that's one of the challenges we really face in that communication space when we're dealing with community in terms of tsunami, because people think of tsunami often as one big wave. And that's how it's depicted in Hollywood movies, right? But it's often not. We were still seeing waves bouncing around along the coast of New South Wales on Monday afternoon, so 48 hours after it had happened. And they were still sizable. They weren't things that you just be like, oh, whatever. It took a good sort of 24 hours plus for the tsunami warnings to be cancelled for the whole of Australia. So I think that's certainly one thing I would say in that space. The other thing I would say is doing the amount of media that I did in that time frame, I found personally really exhausting and draining. I needed a bit of a holiday from my break in my holiday to recover. And I have absolutely no idea how epidemiology researchers have been doing it for 2 years.
Yeah, absolutely. You were everywhere for a few days there. It was like Hannah. Yeah, it was great. You and Heather Hanley as well.
Yeah.
It was awesome. Yeah. It was awesome to see. Yeah. We've got a comment from Marion. She's put together an archive of Tonga eruption and tsunami data on Google Drive. If anybody wants access to that, it looks like an amazing resource for, as she says, teaching or basic research. Awesome. Yeah, that's wonderful. We have hit 2 o'clock, but I'll just do a final check if there are any more questions. If not, we'll bring it to a close. It looks like we're all good. Okay, great. Thank you so much, Hannah. That was a really enlightening talk and really interesting as well. That was wonderful. Thank you.
Thanks for having me.